Hey guys, this is Team 2 for Embedded System Design. My name is Faraz Khan. The other group members are going to be presenting more topics later into this video. First guy is Sam Bear, the second one is John Mert, third one is Bardia Nikpur. And John and Sam, they both worked on the pickup rover, and myself and Bardia, we worked on the dump rover, with myself also leaning more towards the communication aspect of both of the rovers. The overall purpose of this project was to create an autonomous rover system. We have this pickup rover that automatically scans for cylindrical size objects, and it goes to it and it picks up these objects and essentially just puts it in here, and both of these rovers go back to a designated landfill area, sort of like the Wall-E movie. And pretty much the whole purpose of it is just to prove that we can have an autonomous system with embedded boards. One of the goals of this project was to show that the Pixie Cam could pretty much detect objects, right? And with the Pixie Cam being able to detect objects, we were able to figure out a direction to go to pick up objects. We were able to facilitate like following for other rovers and other things like that. Right in the middle, we have two highlighted components. One was a laser ping rangefinder module. This laser ping rangefinder module, it was used to detect how close it was to a specific object. So a Pixie Cam alone isn't able to accurately display distances because of the angles and everything. That's something that Sam is going to go into more detail later. But pretty much we use the sensor to get an accurate reading on how close you were to an object. It was pretty much just a laser sensor that would ping back data and tell you how far it was. And this other piece right here, this is the Actuonics linear servo. It pretty much just lifts up this dump tray and puts it back down. We highlighted these two components because technically without these two, right, the project would not have happened.
So I'm going to talk about the pickup rover. This is the pickup rover. It's made of two pick boards. John will talk more about the motors down here below. My part was more focused on the sensors on the board, on the rover. So front we have a claw. This is our Robot Geek parallel claw. Obviously had to extend it a little bit. That's what this is all for. But it works through a servo using PWM module. Not too hard to use, not too much involved with it. The whole point of it is to obviously grab the trash later down the road. So we make our trash pieces, which hopefully you saw during our demo, are the little yellow cylinders, which we created off of knowing what this claw was like. Improvement would be to get obviously a better claw that would be able to grip other pieces of trash, not just cylinders. Another big piece of hardware is this time-of-flight sensor, which is this blue piece of hardware right here. A time-of-flight sensor is a laser, basically, so it's very similar to an IR sensor, but it instead uses a laser. It goes out, sends a pulse, and when it comes back, it will be able to record the time, and then this device reverts that time to a distance. This device specifically uses the UART interface in order to display those distances through ASCII characters, which makes it much easier to interact with. But what's also nice about this is, the reason why we use this versus an IR sensor is because the cone of vision is a lot slimmer. So we know when a piece of trash is right in front of the claw that it's an accurate distance rather than, say it was over here. If it was an IR sensor, it might read that as in the claw, but not actually in front of it. Also, this piece of hardware was fantastic. Would recommend it anybody looking to take embedded. Would recommend this if you need anything with distances up to 2 meters. This works. Works great out of the box. Would recommend it. The last piece of hardware that I ended up interacting with was this Pixie Cam. Pixie Cam is a piece of hardware that is really good at detecting colors. It does everything on board, so all you need to do is you can press this button, or they have a USB connector that you can work with on your laptop that will allow you to set what colors you want and which signatures it should pick up. From there, it's able to communicate through various interfaces, SPI, I2C, UART. I ended up using the SPI interface. It was much easier for me to use. I2C, I had a lot of difficulties with the pick board. But using SPI, it was relatively easy using some of the built-in software for the pick that allowed interaction with the SPI or with the Pixie Cam. The Pixie Cam works by sending different packets, so you have to formulate your packet, and when you send it out, it'll then send a snapshot back. So basically what it does is every 200 milliseconds, this Pixie Cam will look at what it's seeing, take a snapshot, and then send back the center location, so the X and Y coordinate of what it sees, the height and the width of that object as well. So from there, because Pixie Cam will pick up the biggest object, which in terms is the closest object, it will be able to send that information to the board, which will then be able to tell John's part how to maneuver. I'm also going to talk about the robustness of our implementation. So obviously on both of our rovers, there's a lot of different components. One of our better components is, I think, the robustness. The Wi-Flies are not the easiest devices to work with, but what's nice about the way we implemented ours is, if say there's 2 packets coming in at once, the Wi-Fi will ignore the older packet and just take the newest packet. This is something we had to implement hardware through the UART interface, which wasn't too difficult to do, but ended up helping out a little bit in the end. The major problem with the Wi-Flies is that when there's a malformed packet, so say like I was trying to send some packet of information, if there was, it's sent it halfway built, it's not to Nginx, Nginx would complain and reject that packet, send it back to the Wi-Fi with a 500 error. This 500 error causes the Wi-Fi disconnect, which, you know, it just blinks green and then it slowly just dies out. This can cause a disconnect. This can cause a delay of anywhere from 10 seconds to 50 seconds or so. But at that point, the Wi-Fi just reconnect and everything begins to resume. Also on my end of the devices, there were some issues with robustness, specifically the Pixie Cam. Pixie Cam is really not great at determining the color in different lighting conditions, whether I did it in my apartment or try to test it in the lab, even in different areas in the lab, whether if it was on the benches or on the floor, it created vastly different color signatures. Because of this, I had to sync it up whenever we were going to test or implement it, had to test it up for that specific lighting environment. If there was another camera out there that could do condition all these different color signatures and detection from a long distance, that would be fantastic, but obviously I didn't know one, and hopefully you guys out there can find one. The claw also wasn't great. It wasn't long enough, and it was kind of not what we wanted. We wanted to be able to pick up bigger objects. It doesn't really make a difference, but we wanted to pick up bigger objects, and I can only pick up cylinders because of the way the claw is designed. So coming up with a claw that would be able to grab more varying shapes would be something of interest to us and would help increase the robustness. Other than that, the server interactions worked just fine. Yeah, didn't break too much. There also were some issues with robustness with the dump rover. The dump rover was designed to follow the pickup rover, which it doesn't. I don't know if that was evident by the video. It only follows if it's a straight line. As soon as there becomes some angle turn, it can't follow and doesn't sense that. It's obviously designing some system where we could detect that angle and be able to actually follow the dump rover, or getting the dump rover to follow the pickup rover would be fantastic and thoroughly increase our robustness. But for now, all that it works for is moving in straight lines, which doesn't do a whole lot.
Hi, my name is John, and I will be talking about the pickup rover port number 2 and what it does. My part was mostly about navigation and motor control. I used the rover motors provided by the lab. There are about 6 pins you need to use if you want to control these motors effectively. 2 of these pins are like enable signals for the motors. There are 2 other pins for controlling the direction of the motors. Turning these pins on will make the rover go backwards. The last 2 pins are encoder signals. Each of these motors have little sensors on them that can detect the movement of the motors, and they output a square wave signal. So each time you see a positive edge on the pin, it means that the rover has moved a certain distance. Using these pins, I wrote an API to control the movement of the rover. I wrote 4 functions for going forward, going backward, turning left, and turning right. Going forward and backward functions use centimeters. Turning left and right functions use angles. Forward and backwards functions are accurate from 2 to 100 centimeters. Left and right functions are accurate from 10 to 720 degrees. The main problem I had with the motors came from turning left and right. Going forward and backwards was very accurate all the time. However, turning around was not really reliable. It was affected by the battery level. It would turn more or less depending on the surface the rover stands on because of the friction. My navigation algorithm was mostly dependent on the data coming from the PixieCam and the time of the flight sensor. PixieCam is used to detect pieces of trash. The rover turns around until it sees a piece of trash and tries to center itself to the trash. Once it's centered, it starts moving towards the trash using the distance data coming from the time of the flight sensor. Once the trash is grabbed by the claw, it gets lifted by a DC motor until the dump rover positions itself under the lifted claw. Bardia will explain the movements of the dump.
Bardia and Nickport, I was in charge of them moving the rover to follow the first rover. In order to achieve this target, I used the IR sensors and the DC motors. The IR sensor I use is a distance sensor, which detecting from the 10 centimeter to the 80 centimeters. This distance sensors, which gives us the analog value, and I've used the analog value and input pins and the timer to read this value and then convert it to the distance. I used three of this sensors. The front one for the following the other rover, and then the other two for preventing from the accidents. For the movement, I have used gear motor and magnetic encoder, and also I use a PWM to provide input voltage for the DC motor using a timer and output compare module for the PIC32. Magnetic encoders are used for the feedback of the motor to measure how much rover has moved so far. I use interrupts and clocks for reading the impulses of the encoder, and use these counts to move certain distances and certain degrees as well. The problem which I was facing was we didn't have the good mapping system, and and also doesn't have any reliable motor, and linear and a rotational movement of the rover are not entirely reliable because of the different motor behavior or different surfaces with the different weights. And also the IR sensor that we was using wasn't reliable as well, because the IR sensors usually behave differently.